Hello everyone, we're back with another episode of Computer Vision Talks, and today we're going to discuss self-supervising occlusions for vision with Dinesh Reddy. Dinesh is a PhD student at Robotics Institute at Carnegie Mellon University, and something that I have been talking about almost twice off the camera is that I invited him last year to talk about one of his CVPR papers, but he was waiting to publish another one before he talks about the last two. And today we're going to discuss three of his papers. So it's going to be an interesting talk because it is going to be a journey, but I'll not spoil all of that and I'll let Dinesh talk more about it. Thank you. Over to you.
Oh, thanks, Shambhavi. Thanks for the good introduction. Thank you all for coming to the talk. So most probably this talk will be like how I thought about the problem throughout my PhD and like why I was interested in the problem and like how I solved it. So most of this talk will be about occlusions and why I was excited about it. Like, let's dive into this talk at this point. You can stop me at any point, ask me any questions, and I'll be happy to answer. Okay, so virtually every scene has occlusions. Even a scene with a single object exhibits self-occlusions, as a camera can only view one side of an object or part of the object is outside the field of view. More complex occlusions occur when one or more objects block parts of another object. Understanding and dealing with occlusions is hard due to the large variation in the type, number, and extent of occlusions possible in scenes. Understanding a scene with occlusions will play a crucial role in multiple domains. For example, in this case, the incoming truck can be detected faster, avoiding an imminent collision if the vision algorithms can predict the object when only a fraction of the object is visible. Humans are very good at distinguishing and understanding a scene even when only a fraction of the object is visible, as you can see in this case. Such capabilities give us faster reaction times, and understanding such holistic representation will play an important role for autonomous agents. Occlusions happen in other lot of scenarios as well. Like, for example, if someone is proposing in Disney and then like someone photobombs the shoot, or Arnold can come in between your picture. So disentangling any two objects in a scene is very important in like different other domains, not only in like robotics, but like photography and all multiple other domains. So that's the reason I was like super excited in solving this problem. But the problem was, although vision algorithms have progressed substantially over the years, most of the methods report their failure cases to be caused by occlusions. We show such failure cases for different vision problems like pose estimation, where large overlap between cars or people leads to confusion in predictions of parts, both in top-down and bottom-up approaches. The exchange of key points in these situations stems from not understanding the object interactions. Similarly, such cases can be seen in segmentation as well, both the bottom-up and top-down approaches. In crowded scenes, either people are clubbed together or the detections have too many overlaps. It's very clumsy. So like understanding these occlusions is very important for both these problems. These errors propagate into tracking and segmentation and posing and different other tasks of vision as well. As you can see here, most of the objects in the front, like this person moving around, is tracked well. But if you observe the person in the back where he's climbing elevator is like flickering a lot because of occlusions. Similarly, in case of 3D reconstruction, like the front person is very accurately reconstructed, but if you observe the back, there is a lot of flicker. So these kind of issues happen whenever there are occlusions, and we need to address these problems. So current vision algorithms are very reliant on widely available human annotated datasets. All the way from ImageNet to recently introduced Mapillary datasets have helped improve accuracy in different problems like detection and segmentation. Even 3D reconstruction and pose estimation show very high results, but all of this have only annotated the visible regions, which we can see in the image. Rapid improvement in accuracies have been achieved due to progress of these of vision algorithms using these large datasets. But the failure cases in severe occlusions have been persistent over time. agnostic to strides made on like these average accuracies on COCO and VOC datasets. The reason for these failures is due to occlusions being treated as noise in the average precision metrics. And in most of these datasets, number of occluded objects with large occlusions is much smaller compared to the comparable visible objects. These metrics need to be better modeled for handling occlusions in general. So another major reason I found for such failures is because the methods are heavily dependent on supervised learning methods. But supervising occlusions by humans is very imprecise. We requested 3 different annotators to draw poses of vehicles on the same image. Observe that the annotators pretty much agree on the pose for visible regions, but the disagreement in the pose estimation is larger in occluded regions. Increasing the occlusion percentage increases the amount of disagreement across annotators. So as you can see, like as we increase occlusions, it's very hard to annotate the occluded parts. So using supervised methods is not a very good way to solve this problem. And this is not only with only pose estimation. If you do even bounding box, you can see that with different occlusion levels, the disagreement among annotators. And similarly, even for semantic segmentation. So any task you take, as long as there are visible regions, it's well and good. But as you try to do occluded regions segmentation or detection or pose estimation, the annotations are very bad. Another problem is there are like a lot of data sets which have proposed annotating occlusion regions, like which is in Kitty we call the KNS data set, where there are like 6,000 images out of 15,000 which were annotated with these segmentations of occluded regions. But this is very sparse. Like I think the occlusions are much bigger problem, and these cannot, the number of annotations there are currently on these data sets is not sufficient enough. Even in the case of COCO, people have annotated 5,000 images, but like that's not large enough to learn all kind of occlusions. On the other hand, there are these synthetic data sets which propose using synthetic data to learn these occlusions and these boundaries. But the problem here is, although they are large, they are very synthetic and they don't transfer to the real world situations. So what I'm going to talk about in this talk is, first, how do we learn full object representation, which is like, can I get the poses of the objects in both the visible and the occluded regions, or the segmentations with all the objects, not only the visible but even the occluded parts, so that we have a holistic representation of the scene. In this case, I've been studying which are the best ways to do it, and I figured there are 2 ways to do it. One is what I call multiview supervision, where we see from multiple cameras a single object and like try to learn occlusions. And then the other is a longitudinal, where we observe something for a long period of time. I'll go into the details as we keep going. And another major contribution is I introduced 2 new data sets, which is called CarFusion and Vault, where one of the data sets is for multiview supervision and the other is for longitudinal supervision. Throughout the talk, I will show that evaluations in case of detection or segmentation or reconstruction should be done with respect to occlusions. That is, you should show how much the accuracy drops with respect to the percentage of occlusions in the object. So generally, we just see one metric, which is like AP or in case of detection, and different metrics showing just the accuracy over all the data set. But my general consensus is, if you do that, you miss out on all the cases where there are like a lot of occlusions, and it might not be working so well, and those are smaller cases. So we should always show how the accuracy of your algorithm is based on the number of occlusions. And finally, I show some applications where I show nice visualizations of 3D and 4D reconstruction using these accurate predictions of detection and occluded regions. Okay, so as I was saying earlier, so we have 2 methodologies which I'll discuss today. One is the multiview supervision and the longitudinal. Let's go into what multiview supervision means for occlusions. So given an input view, we want to localize the left arm of this person, which is occluded. The assumption in our case is we have a multi-camera view of this person at the same time instance, and we use some kind of a detector framework and detect the elbow in all these images. And then we run a structure from motion on this particular pixel using this camera observations. As you can see, we get a nice trajectory of the object. Now the assumption is we project it back into the input view, and that is our supervision signal. And this way we are able to localize the key point accurately when occluded as well. So this is what I'm going to use to learn occlusions in all my multi-view setups, or this is the basic way I propose to do it. So to do this problem, we introduced a car fusion data set where we went around and captured 10 intersections with 20 handheld cameras. So to get this multi-view information, we need like a large setup of cameras. And to do this in the wild, we used like 20 cameras to do it. So I'll show you one example of Fifth and Craig is what we call at CMU, which is an intersection very close to CMU. And we just went and we captured these videos at the same time instance from all these cameras. And nearly 13 people holding 2 cameras went around the sequence. There were some cameras on the car. So we just went around and captured the whole scene. So this is how we created this large data set. And similarly, we went and captured in different intersections. I'm just showing a simple one camera view of all these intersections. So we used nearly 20 iPhones, Samsung Galaxies, and GoPros to capture all this data. So it's a nice data set if anyone wants to use it. So we captured a total of 2.5 million images, and we annotated 53,000 images out of it with both the occluded and the visible regions, as you can see on the top right. So the occluded regions are annotated as red, and the visible regions are annotated as green. So this way we are able to even distinguish which is occluded and which is not, which is very useful later on in different pipelines. And for all of this, we have done camera pose estimation, so you can do 3D reconstruction and other things automatically. So what is this multi-view supervision? So how do we solve it for our problem? So we have this input video streams, and then we do a 4D reconstruction of the environment. Once we do the 4D reconstruction, we project it back into the views, and then we have for each car, we have the complete 3D representation of the object. And then using the input views, we train what I call as occlusion net. And using this occlusion net, we compute the loss between both the visible and the occluded regions. So let's go into how I do 4D reconstruction. This is one of my papers, which I'm going to talk about now. So given all these videos, we are able to do this accurate reconstruction of people and cars. I'll be talking more about this work at this point. So this is what we call as Track, which published at CPR 2021. So we quickly give an overview of previous work addressing the problem of 3D pose estimation and how we are different from it. We start with single person 3D pose estimation. All the methods proposed can be divided along the lines of monocular and multi-view based methods. But these methods learn the 3D pose in an end-to-end fashion for a single person, but fail to extend to multi-person scenarios as they cannot model people interactions. Similarly, we show methods which take multiple people which can reconstruct multiple people, but all of these are monocular based methods. These work very well, but these are all instantaneous and they do not take the temporal information into picture. There are methods which have done the complete 3D reconstruction from videos as well as multi-view. But the problem is all of this were learned in a piecewise manner. They learn detection separately, segmentation separately, and different parts of it individually. Instead, our framework takes an input videos from all the thing, and then has an end-to-end trainable framework. And then we are able to predict like very accurate poses over detections as well as time. So the first part is, given this input videos, we have a backbone, which is a HRNet, and then we convolve all this, we deconvolve these background detections into a 3D grid, which we call as the person detection grid, and we run a 3D CNN on top of it to do detections of each person. So these detections are, you can think of it as very similar to 2D detections in mass car CNN or any framework, but all of this has been ported to 3D now. So given all this input video, we have a 3D person detector framework using 3D convolutions on a grid. So once we have this, we have each person detected in all the videos. So we take each of this person and we create a 4D temporal volume around him, which I am showing here. And then we do 4D convolutions on this so that we get per person descriptor at every time instance. How we use them? So given all these 4D descriptors of the person across time and space, we are we need to do a tracking algorithm on top of them. So at time t and t plus delta t, there are like multiple people in the scene. So the problem we are solving next is the people tracking person, where we associate which ID at time t corresponds to which ID at time t plus delta t. So to do this, we train a graph neural network based methods, which I am not going much detail into, but it is basically an association algorithm which we develop. And so using this association algorithm, we are able to assign which person belongs to which other person at different time instances. And once we do all this, we are able to associate time t and time t plus delta t persons across time. And using this, we create a large temporal descriptor of the person over the whole period of time. So given at t 0 to t 10 minutes, we can associate the person across all the time, and we have a large descriptor of the person moving around the scene. Once we do this, we combine all this descriptor and we deconvolve it back into the 3D space. And we are able to estimate the poses in 3D space as well as time. So it's a continuous vector of the person, each key point over both the time as well as space. So we have 3 losses to train this. So given the input, we predict, we compute the detection loss, and then the tracking loss, and then the pose estimation loss. So using this method, we are able to get like very accurate 3D and 4D reconstruction of objects. So the advantage of using this method is we are able to show large improvements on like multiple data sets for the 3D pose estimation problem. On human 3.6, we are able to do 2.1 MP JP improvement over the state of the art. Similarly, 10.4 mm on panoptic. Actually, this is a large boost. A lot of people has been asking me why this is. The reason, I think the major reason is because we use a 3D or a 4D volume, and since this data has a very high frame rate, we have a very smooth trajectories computed automatically, since our optimization is both in space as well as time. I think in general, we should use a space and time optimizations to do 3D estimation. Similarly, we show 0.7 on campus, which is a very famous 3D pose estimation data set as well, and 1.2 on shelf. We evaluate all of these evaluations on robustness of the algorithm to the number of views as well. Here, since instance represents compute at each time instance independently without using temporal information, observe the increase in accuracy with the addition of views, showing that more views help produce robust reconstruction. Using our 3D spatiotemporal features, we reduce dependency on multiple views, as can be seen from the higher accuracy in tracking and reconstruction.
Hi, Dinesh.
Further, yeah.
Yeah, I have a question. Like for the test data, do we assume that we have access to multiple views? Because the
Yes.
car fusion data set. So
yeah.
do we assume that we have access to this information for the test data as well?
Yes. So how I split the data is we have 10 intersections being captured. I only train on like 8 intersections and 2 intersections are used for testing. So it's a completely new scene. And all the time we have a multi-view setup. I mean, you can do evaluations on single camera as well, but in general, we have a multi-view setup all the time in the wild.
So in case if you want to extend it to single view scenario.
Yeah.
So then how can we, how is it possible to extend this?
So this is what you're asking is a simpler version. The multi-view is a harder thing to capture, but the reason we do multi-view is because we want that supervision from multi-camera systems. But how I see is you can take any camera and you can run your algorithm in the single view. Use multi-view as a supervision to say whether that whatever your accuracy was, whatever your algorithm accuracy was accurate or not. So generally, I look at multi-view as just a supervision signal, but all my, so in the later talk, I'll say that I have occlusion net, which is a single view algorithm as well, where we use multiple views to supervise, but everything can be done single view as well.
Okay, okay, thank you.
Thanks, yeah.
So there is another question. Sorry, Dinesh. There's another question in the chat. Sai is asking, how compute intense is this method?
So this I think is very compute intense. The problem, I had a lot of GPUs when I was doing this. So I was working at Amazon and then like we used A100s and like 8 of them. It is definitely very compute intensive because people have only thought about 3D convolutions. But once you think about 4D convolutions, I think it just, the memory explodes and it is very heavy. But I think there are methods to reduce the compute as well. People are thinking about it. A better 3D representation might help. Yeah, but as of now, I think it uses like A100s, 8 of them to train this algorithm.
Okay. And were there any optimizations that were performed?
I think in this case you just have to do a very generic. So when you think of a kernel, you just don't do a 3D kernel. You do a 4D kernel. So it's a very simple addition. I don't see a lot of change from like the previous methods. There is no specific optimization. We always use like this generic 3D convolutions, 4D, whatever the learning based methods. Yeah, but the harder part is getting the data into the pipeline and like training new. It's a more data intensive task.
I see. Yeah. And there's another question that is asking, is there any ablation where the contribution of HRNet versus the older network in the SOTA method is being studied?
I think, yeah, I think we were agnostic to the background because for me, when I say backbone, I just took HRNet or whatever the state of the art and you could train the network irrespective. So I was not worried about what the backbone is at this point. Because any backbone, maybe now there are HR transformers or like something new, new deep learning pipeline keeps coming up all the time. So I didn't do an evaluation with the previous backbones as such, but I did a lot of evaluations on how to improve your 3D compute, which is like the main contribution in the paper.
I see. And the last question for now is from Mohit. He's asking, is like transfer learning possible with this architecture?
Yes, I show later that we are able to predict or learn on panoptic and like predict in like different other data sets. Like all these accuracies I'm showing are trained on like only panoptic and they are able to like transfer to a different data set automatically.
Awesome.
Yeah, so that's the advantage. Like if you do anything in 3D or 4D, generally the transfer is much easier than if you like learn in image space, because image has like much more features. Anyway, so if those are all the questions, I'll just continue. So yeah, as I was showing, this algorithm using this temporal as well as tracking helps the reconstruction faster. So Panoptic has hundreds of cameras, but we are able to do much better accuracy with much lesser number of cameras at this point. So I show some results. So you can see like we are able to accurately reconstruct people in the wild with like a lot of cameras, like where you are having like people walking around, and we are able to accurately reconstruct everyone. This is a nice data set as well by Min in 2019, where they captured all the people from different cameras. And then similarly, I show accuracies of cars being reconstructed in like different views, and like you can see like these trajectories of people, cars going around. So the advantage is, again, these are very hard problems. Although like autonomous driving, people are doing it very accurately, we are only doing it with cameras. I think that's the major takeaway. Observe that we have like smooth trajectories where we are able to reconstruct the whole scene from like different views. Similarly, we went and like we did this across all the intersections which I told earlier, where we have like nice 4D reconstructions of scenes. So the major advantage is we want all these reconstructions to be used to learn occlusions. I think that was my basic aim, to do all this 4D reconstruction, but these can be used for different other tasks as well. So going ahead, as I started, we were like multi-view self-supervision. So till now we saw how to do 4D reconstruction. Now I'll talk how we are using this 4D reconstruction to do this occlusion net and like training for occlusions in general. I got a question earlier, how do you do for single view? This is what I was talking about. So given an input, occlusion net only predicts at every time instance, but how I look at this multi-view data is as a supervision to like learn automatically, instead of you going and annotating, or humans annotating stuff. So generally, as I was saying earlier, human supervision for occluded is like not accurate. And then in our case, we have this nice data sets where we are like able to show ground truth classification of occluded and invisible. So the first question is, how accurate is this prediction from mass Gaussian? So you just take a naive mass Gaussian and you run your mass Gaussian key point detection. Can mass Gaussian distinguish occluded to visible is the question. And as you can see, there is a huge overlap between the confidences of the scores between mass Gaussian prediction for visible and occluded. So this emphasizes that you need to learn occlusions specifically to like better understand how to predict key points in cars or different other regions. So as we go ahead, we see like using our framework, instead we are able to get a better ROC curve for occlusion compared to 2D GNN. With this just signifies that like you need to learn occlusions explicitly in all these networks. Like generally they only, you irrespective of the key point, you just predict them. But I think just by adding a simple constraint, whether it is occluded or not, helps your prediction of key points much more accurately. So as I was saying earlier, we have the input, we just run a mass Gaussian based framework, and then we do we show some classification accuracy. So using mass Gaussian, if you just threshold it by 0.5, we get these as the regions as occluded and not occluded. But on the top, you can see that person is occluding the front headlight of the car, but mass Gaussian is not able to distinguish them. But in our case, using our 2D KGNN framework, we are able to distinguish objects whether they are occluded or not. So how our pipeline works is, given an input image, we compute heat map loss for all the key points, not all the key points, the visible key points. And then we run a 2D KGNN on it, which is a graph neural network. which takes all these key points and predicts which are occluded and which are visible. As you can see in this case, the whole car is visible, but there are some parts of the car which are occluded, like the back headlight or back wheel, which it is able to predict automatically. And this we call a edge loss. Edge loss is the difference between the visible and the occluded regions. And once we have this, we are able to run a 2D KGNN, which corrects this localization of the occluded regions. So as you can see, here we have these regions wrongly predicted, but using our graph correction network, we are able to correct these occluded regions. But how do we get supervision for this? As I was saying earlier, it's hard to annotate. So we use our 4D reconstruction pipeline. So once we have this 4D reconstruction, we call it trifocal tensor loss, where we have multi-view supervision to do it. So how do we do it? So you have this occluded view and you want to localize like this white car's key points, but you have other views of the same car. So here you are seeing it from a different view and below another view of it. So you localize the wheel of both of this of the same car in these two views. You project it back into the 3D, and then you project it into the input occluded view, and then you localize. So this is what when I say a trifocal loss, this is the best way to give supervision, because even if I annotate it or any other method, I will never get very accurate localization. But using this method, we are able to get a very accurate localization of that key point using multi-camera systems. So we use a trifocal loss, which is just whatever I explained earlier. We project like these 2 points into the 3D and project it back into the occluded view, and we minimize this loss with respect to that key point. By doing this, we are able to do this nice 3D and 4D 3D reconstruction of these key points. And the other advantages in this method is, once you have a representation of key points, you can automatically go from 2D to 3D, which we call the reprojection key point loss. And this is completely self-trained. All you have to do is give the key points. You can predict the mean shape of the objects and the camera pose. And if you use these two constraints and project it back, you can minimize the loss with respect to the input view. This way, we are going from 2D key points to 3D key points automatically. So using this method, as you can see, we have like a lot of reconstructions of car key points, and like across, we are seeing that although they are occluded in multiple views, we are able to predict like very accurate localizations. So as you can see, mass Gaussian based has very bad key point predictions, because visible points, mass Gaussian works excellently well. Like you just go, you threshold it 0.5, you see all the visible points. But if you plot everything, it looks like very bad, because they were never trained to predict occluded points. But instead, if you just use our occlusion net framework, you are seeing that the localization of occluded points is very accurate at this point. The advantage is, yeah, as I was saying, multi-view supervision generally helps. And as you can see, with different kinds of occlusions, with different objects occluding it, we are still able to do very accurate localization. And using this, we can directly go to 3D, as I showed earlier, and we show same reconstructions across different occlusion percentages. So again, coming back, how does the accuracy change with occlusion percentage is a very important question I always ask. So as you see, number of invisible points is the occlusion percentage. As you keep increasing, like mass Gaussian falls, but our 2D KGNN gives better, although it also drastically reduces. But just using this 3D constraints, you get like a much higher accuracy. And we show with the different percentages of the threshold of that, you can you observe that our method is able to do, like occlusion net is able to do much better accuracy than mass Gaussian in general. And I slice the data at one occlusion percentage, and I show you how the graph looks. So As you see with the number of invisible points increasing, you clearly see like the accuracy increasing as well. Better accuracy in case of our occlusion net, which is the red line. So generally, if you slice your data with occlusion percentages, I think you better understand how robust your algorithm is with respect to different hard case scenarios. And I show another thing is that since we use this and we have both the human annotation and multi-view supervision, we can analyze how good the human annotators are. So the top is an example of a human annotated data set, and the bottom is a multi-view prediction. You observe that like as we keep human annotators generally annotate with like 0.2% accuracy error, and we show an example of a very badly human annotated example as well. And most of this point lie within 0.3, but it's a nice analysis we did just to show that multi-view supervision is better, and we can evaluate how good human annotators are with respect to like using geometric constraints. So using this method, we train, and you can run it on any camera. You just observe that like at this point, you take our occlusion net algorithm and you can like run it on any camera, and it like gives very accurate reconstructions. So in summary, for multi-view, it is very good to generalize to new viewpoints. Hence, it helps in analyzing human annotations as I showed earlier, and can learn self-occlusions as well, where but it is very hard to extend it to new locations because this capture setup is very hard. And then there is a lot of compute needed for doing this 4D reconstruction. And you need the camera pose estimation and stuff. So it's like a lot of framework which needs to go in, but it is very accurate to do occlusion statistics. So that's the reason there is another paradigm which I followed, which I call longitudinal self-supervision, where given these like we were looking at multi-view. Now I look at like how to look at time and then figuring out occlusions automatically. This is much faster. So in general, what is longitudinal supervision? A lot of self-supervision. A lot of people will ask me. So given an input frame, generally algorithms just predict what is visible. Like if you take any deep learning algorithm at this point. But the thing is, if you see the scene for a long time, you observe that objects keep changing. As you see here, this car left, and then the green car became more visible, and then even the white car left, and then the whole object is completely visible now. So this is like the completely unoccluded object has been detected at this point. And can we use this as a supervision in our previous frames and like predict the object more accurately? So from green, we are able to do this yellow kind of a prediction. And similarly, we are able to, as the time keeps going, maybe other cars left and the red object is also completely visible. So even that can be used back to train occluded and non-occluded regions to get a complete holistic understanding. So as you see, like this is explicitly used as supervision in our framework. So given our input view, now we have a complete A model segmentation of these objects just by observing it for a lot of time. To do this, what did we do? We created this large vault data set where we captured 100 videos of 4K and like 1080p resolution cameras across different cities. So, and we have been capturing it for a long period of time. So I'll go and show you one example. Like we captured 20 high resolution cameras in Pittsburgh, where this data is captured for 3-second bursts at 30 FPS every few minutes. And this stores nearly 5,000 images per day for a year. So we have a very large data set at this point where we have this cameras being captured for a long period of time. And we need not constrain ourselves to just our own cameras. You can just take any YouTube camera. Here you observe like we captured in Thailand, where people are walking around and in different like lighting conditions and stuff like that. Similarly, we can go and we captured in Europe and Russia, where there is like snow and like different weather conditions and different camera angles. So it's a very nice large data set with like different views and stuff. So how does the captured views look? This is how the views look. So you go, you like look at all this data like over time. There is rain, there is like people, there is like objects interacting. There is no constraint whatsoever. It's a completely in the wild data set. And I think it's very useful to learn occlusions and different other tasks. This was submitted to CPR 2022. If you're interested, you can download and like play around with the data set as well. So what do we do first? The simplest thing you can do is just do a background image computation, like which is like we just take all these videos, find the median, and then you are getting this nice time-lapse videos of objects where we only have the background. So the task which we solved in this paper is it's very hard to understand objects and occlusions in general, but it is very easy to find an unoccluded object. So in our case here, you can see that there are 3 unoccluded objects, but our algorithms in general give like all this detections. Like you run any detector and you get all these nice objects, which is great. But how do so there are only like some of them which are like completely unoccluded. Like for example, if there is no interaction between any other one bonding box with any other bonding box, that's an unoccluded objects. That's a very easy thing, like it's one line of code or something like that. And then how do we find unoccluded objects when they are object interaction? So you look at this line as I'm drawing this green line. So this green line, if it is larger than a threshold of the bonding box, generally it is those objects are occluded, and anything which is not is unoccluded. That's how we distinguish unoccluded objects from occluded objects. This way we are able to get all the unoccluded objects in a scene automatically out. So this is a very simple algorithm. Like you can just go and like write it in like 10 lines of code. This way we are able to mine like hundreds and thousands of unoccluded objects. As I'll show here on the left, you see that we are able to like mine all these unoccluded objects automatically. And on the right, we collect all these unoccluded objects into a large database. The reason we are doing unoccluded objects is because once you have these can be used as supervision to learn when there is like occlusion. So how do we do it? We have the background image which I showed earlier, and then we are able to like nicely put these objects back in the same locations where we detected them, and we are able to create this semantic segmentation maps of occlusions automatically. So on the left you see objects being placed, and on the right, as the layers keep going, we are able to see the objects and their segmentation mask. The darker means there are more occlusions to that region. So this way we have a holistic representation of the whole scene now. So we do this for all the cameras in all the objects. So we have this nice mosaic where like we have all the objects with different levels of occlusions. So we train this network at this point. So how do we train? So we have this input image where this object is occluded, but we just don't want the visible regions. We want to see what is behind it, what is in front of it. So given this object, we call this as a model segmentation. So we want the complete segmentation. So how did we get this? We used the earlier ground truth which I showed, and we are getting the full object segmentation. Similarly, we get the segmentation of the occluder and then the occluded, which is like the object behind it. So this way we are learning the not only just visible region segmentations, we are learning what is behind, what is in front, and like the whole complete scene just from whatever is visible. So how do we train this network? It's a very simple network. It's not like anything fancy. We just take a input image. We have like a box detection, and then we have three, similar to how mask Gaussian has like a mask head or something like that. We have three different heads, what we call as a occluder, which is the object which is occluding the other the objects of interest, and then the occluded is an object which is behind all these objects. So generally I believe there are three different components of every bounding box, and these two play a very important role in predicting the actual object segmentation. So we have these three networks which predict all the three layers of the scene. And we have supervision from our longitudinal supervision, where I showed that layering algorithm. And we train the network to predict all these three layers, and we are able to get like very accurate model segmentation. So we speed up our training. Generally, using the earlier detection algorithm, our algorithm is very dependent on the number of unoccluded objects detected. So as we keep going ahead, like we train across, we observe that we can learn this algorithm within 90 days. But if you just use tracked objects and you do the tracking algorithm, we are able to learn this framework to do better predictions in like much lesser time, like which is like in 14 days. Another major contribution in this is, I think, the stationary vault object-based evaluation is what I call it. So it's very hard to do segmentations of complete objects in a scene. But in our case, to evaluate, we use what we call as stationary object-based evaluation, where we just take an object which is stationary and it is being occluded by other objects. Having a consistent segmentation as is our metric to show that even during occlusions, our algorithm is more accurate. So again, coming back, as I was saying earlier, we always evaluate with respect to occlusion percentage. As you see, with increasing occlusion percentage, mass Gaussian drastically drops. But in our case, we are able to do a model object using our a model object pipeline. We are able to have much robust accuracies. And by adding the occluder layer and ours, we are able to do much better accuracy with different occlusion percentages. I think this is a very important takeaway, because as you see, people have to start thinking about occlusions as a very important criterion in all their algorithms, because this is very generic. And we show some evaluations on like different other data as well. You can see on the left, just using this Swin transformer mass Gaussian paper, you see that the segmentations are not that accurate when they are occluded. Multiple people are combined and stuff like that. But in our case, we are able to get like very accurate segmentations. On the right, even for cars, you see like the top two cars, they are similar colors, so they are being combined. But in our case, we are able to segment them out and get like a nice A model segmentations as well. We show more results, and as you can see, they can be run on videos, but we observe a very nice, neat segmentations when they are like multiple kind of occlusions, like people walking and stuff like that. I think this is like kind of some more results on cars. Generally, this helps a lot in tracking. The tracking fails because you are only seeing a part of the object, but now since you have like a complete A model representation, you can track objects better as well in the future. Similarly, we show results on like people interacting with objects. So yeah, such kind of frameworks are like very helpful in like different settings. I think at this point, I just had like one more slide, maybe.
Or maybe you lost it.
Once again, I just wanted to show like the key insights. So in the end, what our algorithm shows is like we show end-to-end 4D reconstruction, reduces dependencies on a number of cameras. So you should always learn like in an end-to-end framework. Generally, human supervision is inaccurate, is what I believe, for localization of occluded things. So always think of learning anything with like a lot of occlusions in a self-supervised manner. And then I think it is very easy to do unoccluded object detection, I think in general, then like you trying to like do all this tasks simultaneously, and then combining back is, I think, a very easy way to do stuff. So I think in general, this I think is a three major takeaways from like whatever talk I gave. Um, um, and I think I need to thank all my collaborators who helped me. Like this work was not done just by me. Like all of these guys have like contributed a lot. Mainly my advisor. So I think that is also a very important takeaway. Like always find like good collaborators. So I guess that is it. If you have any questions, you can ask me at this point.
Awesome. Yeah, please feel free to pitch in your questions in the chat box. However, like the talk, the challenge it solves and the simplicity with which you have put everything is no comparison. Like, yeah, it was very understandable, very understandable. When I was reading paper, maybe because it's a new domain to me, I still found it, harder to grasp things. But yeah, this makes it super clear. And how did you land upon this topic?
So I think in general, how I started was I just went and like I was very excited in my PhD. I was like, I'll do a very hard problem, and I started capturing this data. And I think once I started running things, whenever they failed, I was like, it always came back that like occlusions were causing the failure cases, and like it was a repeated theme in whatever I tried doing across time. So I was like, okay, let's just sit and like solve occlusion as a problem in itself, and maybe that would be a nice, interesting thing to like show people. So I think that's how I ended up like with this problem.
That sounds good. That sounds good. Yeah, that's like genuine intention to solve a problem. Okay. And are you near to finishing your PhD soon?
Yeah, I just proposed like 4 months back. Maybe I'll be done by the end of the year or something.
Awesome. Yeah, because I think this is a lot of work. So I was just curious if you'll be summarizing all of this into a thesis soon.
Yeah.
And do you look forward to work into academia or industry? Oh, I'm sorry, these are two questions. I'm just curious.
I mean, at this point, I'm like open. I think it's just wherever I get to do interesting problems is what I'm looking at. Like wherever I get an opportunity, I think I would go with that more than like, I don't see a difference between academia, industry, or anything. It just, am I solving an interesting problem is like, I think the bigger intention for me at this point. Yeah.
And how would you say that the prior literature, like how much would you say the prior literature already existed in this domain?
I think occlusions is something people rarely look at. I won't say they haven't, they have. For sure, there is a lot of people thinking about this for a lot of time. But it's always in an indoor setting or in some learned space, or so it's very hard. So this took me a lot of time. It's like just the setup takes a lot of time. I think that I think is what is the major takeaway from my thesis, but I won't say like I'm solving it completely. But previously people have tried it in much simpler ways is what I think, and this will just push the boundaries. What I felt like that to solve it well, data is more important than like algorithm. Like that's why I don't go much into the algorithms at this point. I was mostly showing data and like how to capture, and those I think are like much important problems for this task at least. At this point, yeah.
And like if I'm trying to put it correctly, just if I ask you that the working in a domain which is comparatively untouched by people versus working in a domain where fast track research is happening, like if you don't publish in 3 months, someone has already put it out. How do you compare them?
So for me personally, I see it as a bar of risk. A lot of people don't want to take risk nowadays, and they want to go for those easy publishable things, which is fine. But like the larger risk you take, the longer the reward will be, is my general ideology. So I generally spend a year on any project I do. I don't even think I ever submitted in like 3 months or 4 months, at least during my PhD. I generally spend at least 1 year on my problem, any paper I submitted. So it gave me time to think as well, because I was not in a hurry to submit. So I think that will go a much longer way. But there are sometimes something clicks very fast and you want to submit. So that is also fine. But even if something clicks fast, I think if you spend time on it more, you will make it better over time. So I generally feel time will always like give better results. Yeah.
Sure, time gives an edge over the speed. Yeah, interesting. I think that was it from my end. The questions like I was, and yeah, one more. Just last one. Was there any point during your PhD when you felt like, okay, now this is not working, and I'm not sure what am I doing, and where is this research going? Did that ever happen?
So for me, I was publishing every year one paper, and like somehow it was like going with the flow. So the thing is, things fail all the time, but I was never discouraged. The thing is, the more it fails, that means lesser people have done it. So I was very happy. So that means if it is working very fast, I generally feel like more people have done it. So I was like, I won't be more happy, I guess. So it's a relative thing. So either way, if it works, or it fails, it's good. Something, you are getting some result out of it. There is no point being discouraged, I think, in general, like in your PhD, is my perspective, but up to you. But generally, your advisor needs to be on your board. I think advisor needs to support you throughout. Like if not, like I think it's much harder. But yeah, my advisor was like super cool. Even if I failed or something, is like completely fine. Yeah.
That sounds good. Okay, that's nice. Thank you so much. This was one of the best discussions that we have had. Like it was nice, an end-to-end story kind of a thing. So yeah, I really enjoyed it, and I'm sure everyone else would have been enjoying too. Thank you for agreeing to give a talk. I'll put this on YouTube and share a link soon.
Okay, thank you.
Thank you so much.
Okay.
Thank
Yeah.
you. Thank you.
Thank you.
Bye bye. Have a good day.
Bye.